Hello everyone, I am Thilini Bandara from National University of Singapore. On behalf of all the co-authors, I'll be presenting our work REVAMP, a systematic framework for heterogeneous CGRA realization. CGRA stands for coarse-grained reconfigurable array. It's coarse in granularity, meaning the reconfigurability is at word level. CGRA consists of an interconnected array of processing elements. Typically, it has a global data memory for on-chip data storage and host interface to communicate with the main processor. Each PE will contain a compute unit, instruction or configuration memory, PE local storage, and a router. Operations are mapped to CGRA PEs in a spatio-temporal manner, which is another major difference from FPGAs. CGRAs are fully software scheduled, and thus the compiler is fairly complex. Let's analyze where CGRAs stand in the accelerator world. In terms of power efficiency, CGRA lies in between FPGA and ASIC. As FPGAs are bit-level reconfigurable, they consume more power and less power efficient, compared to CGRAs which are reconfigurable at the word level. Application-specific ICs or the dedicated hardware gives the optimal power efficiency, but they are not flexible. Hence, they are associated with high non-recurrent engineering costs, where CGRAs on the other hand are flexible. In a nutshell, we can say that CGRAs provide good balance between performance, power efficiency, and flexibility. If we look at the application domains, CGRAs are ideal for those with tight power budget, especially the applications at the edge. CGRAs are now emerging commercially. SRP from Sampson, TRP from Renesas, and Plasticine from a recent startup Sambanova Systems are few such commercial CGRAs. HiCube CGRA was designed and fabricated in our lab, which we are currently experimenting for deployment in real-time edge computing systems. CGRAs are efficient in accelerating loop kernels. Compiler's role is to statically generate the optimum spatio-temporal schedule for a given application kernel. It will first convert the annotated kernel code to a dataflow graph representation. Generated dataflow graph is then mapped to a CGRA exploiting inter and intra-iteration parallelism. Figure shows such a generated schedule. Once the static schedule is successfully generated by the compiler, it is loaded to the configuration memories of the CGRA prior to the execution. Now let's explore the homogeneity in a CGRA and its impacts. Traditionally, CGRAs are homogeneous in nature. It has a uniform distribution of compute units, uniform local storage, and a network providing equal bandwidth to each of the PEs. We carried out experiment to see the resource distribution of traditional CGRAs and how much of the resources are actually being utilized. The diagram on the right shows area and power distribution of the main elements, local memory, compute, and interconnect, and the highlighted portions represent the resources used for actual work. It is evident that resources are highly underutilized. One major cause for this underutilization is the homogeneous nature in CGRA, where the compiler fails to optimally utilize the resources. Moving from homogeneous design space to a heterogeneous design space is one alternative to reduce the resource underutilization. In the homogeneous environment, the PE array is uniform and less specialized, but it is easy to handle. Such a generic homogeneous CGRA is good for all application domains. But in edge computing, we have the opportunity to specialize for a specific application domain with a well-defined set of applications. A heterogeneous CGRA that is well suited for the specific application suite while still maintaining significant generality is ideal for such situations. But then how do we design such an optimal heterogeneous CGRA, starting with the homogeneous one? It is a huge design space to explore, complicated by the fact that we need to modify the compiler to the architecture to get cycle-accurate performance estimation and then synthesize the hardware to get power and area estimates. This is where REVAMP comes in and provides an automated solution to this problem. REVAMP enables automated design space exploration for heterogeneity, deriving the Pareto-optimal heterogeneous CGRA. Additionally, REVAMP allows architects to explore a wide scope of heterogeneity, covering all the microarchitectural elements, compute, interconnect, and memory. Given a target application kernel suite and a reference homogeneous CGRA, REVAMP searches the design scope and derives a Pareto-optimal heterogeneous architecture. Framework selectively applies individual optimizations at microarchitectural level in terms of compute, interconnect, and memory. Generated architectures are then synthesized to estimate the power area values. Heterogeneous CGRA Compiler will map the applications in the target suite to measure the performance on the generated architectures. It will create multiple such heterogeneous architecture templates of different levels of heterogeneity, which will be compared in terms of performance, power, and area to derive the Pareto optimal design point. Next, I'll go through the individual microarchitectural optimizations that we propose. First element is compute. In a homogeneous CGRA, we have fully fledged ALUs in each PE with uniform compute capabilities. Those will be converted to more diverse compute units supporting only a subset of operations in a heterogeneous compute environment. We first categorize all the operations supported by homogeneous CGRA into subclasses, where each PE will support one or more operation class in a heterogeneous setup. The table shows such categorization. There are 5 compute types: adder, multiplier, logic, comparator, and memory. In order to decide the distribution of these compute classes, we analyze the operation distribution in the input kernel suite. We keep the PE compute class distribution proportional to the distribution in the application suite, but still keeping some buffer to ease the compilation. To decide on the operator class placement, we guide the compiler using hotspot indexing. Each PE will be assigned with the hotspot index, where higher indexes will get more compute resources. The figure on right shows such a heterogeneous compute distribution. In order for the compiler to allocate heterogeneous resources efficiently, a cost model is used to keep track of the scarcity of the resources during compilation. Next is the interconnect. We look at 2 aspects in applying heterogeneity here. First is to convert the fixed width interconnects in a homogeneous architecture to a heterogeneous bit width interconnects. One such implementation is to keep the internal data paths, that is the data paths within the PE, to full bit width, and the data paths connecting the PEs or the external data path to half the bit width. Figure shows implementation of a processing element with such variability in bit widths. The single fully connected crossbar is sliced into 2 crossbars, one fully connected and one semi-connected. Each of the crossbars is now half the bit width. This design will give area and power savings in the crossbar as well as by reducing the size of the external data path registers. Heterogeneous compiler needs to properly schedule the data transfers without degrading the performance, which I will explain in the next slide. In a heterogeneous bit-width setting, we can diversify the bandwidth allocated for data transfers. Since the external data path bit-width is half, we slice the data elements to LSB and MSB. We can have single-cycle data transfers as well as 2-cycle streaming data transfers. Let's see an example. Consider the data flow graph shown here with critical and non-critical edges highlighted. Assume the CGRA has 4 PEs arranged in a mesh. Let's first see the homogeneous scenario. In such a scenario, all the data transfers take single cycle, hence a single execution will take 3 cycles with II value of 2. II value is the number of cycles in a steady state, which is a performance metric for the compiler. Assume the data flow graph is executed on a CGRA with streaming enabled, where data is sliced, and MSB will follow the LSB transfer. PE needs to stall until both MSB and LSB transfers are complete, which will reduce the performance by increasing the II value. This impact can reduce with pipelining the MSB and LSB transfers such that PE does not get stalled. In the example, it has the same performance as in homogeneous case. If there is sufficient wires, it is possible to send the MSB and LSB portions in 2 different paths such that they reach the destination at the same time. Heterogeneous compiler will handle all these optimizations and will allocate bandwidth as and when required. Last element is the local memory. 2 types of local memories can be seen in the traditional CGRAs. One local data memory and one instruction or configuration memory. A straightforward way to introduce heterogeneity is to diversify by the memory sizes. Going beyond, it was seen that there is a homogeneity within the configuration memory itself. Single configuration word mainly contain constants, opcode, and router configs, but they have different variabilities. A lot of invalid or null entries are added in homogeneous structure to combine different configurations to form a single configuration word. We optimize this with a decoupled configuration structure, introducing heterogeneity within. Figure shows such a configuration structure where each type, constants, opcode, and switching configs will have separate storage. There is a common bitmask predicate register which indicates whether the configuration switching is required, and the individual memory pointers will increment and load the new configurations to the configuration register only if it is required. Compiler tries to minimize the switching of configurations such that configuration can be latched for a longer period of time. This will allow the individual memories to compress further, reducing the footprint. In addition, decoupled configuration structure allows more control like clock gating the individual memories, which will save more power. Next I am moving to implementation details. REVAMP has an architecture generator and a heterogeneous CGRA mapper. Both are developed in C++. Heterogeneous mapper is developed on top of Morpher CGRA mapper framework. A configurable system verilog code defines the architecture. Along with the compiler-generated parameters, it will create the final heterogeneous RTA. It is synthesized using Synopsys Design Compiler on 22 nanometer technology nodes. We performed experiments on 3 prominent baseline homogeneous architectures derived from Address, HiCube, and SoftBrain. We use applications from MaxSuit, Polybench, MyBench, and Cortex-Suit benchmark suits in preparing the input application kernel suite to REVAMP. Design space exploration with REVAMP. This shows the design space for deriving the Pareto-optimal heterogeneous architecture given homogeneous HiCube and an application suite with 5 applications. The generated design space has multiple heterogeneous architectures with different levels of heterogeneity. Power and area numbers are directly obtained from RTL synthesis, which throughput is determined with the II value obtained from the mapper. Out of the design points, we choose the design highlighted in red as the Pareto optimal in terms of throughput, power, and area, which is shown in the right-hand side diagram. It has diverse compute units, internal data paths of 33-bit and external data paths of 17 bits, and different memory sizes. Similarly, we perform design space exploration with REVAMP on all the three baselines using the same kernel suite. Table summarizes the optimizations added on each of the baselines. Address has a simpler network without ALU bypass paths. Hence, any heterogeneous interconnect optimization adversely impacts the overall performance. Thus, it does not make sense to apply. HiCube does not have a local data memory in PE, and SoftBrain does not have a configuration memory as the PEs are not time-sharing. If we analyze the utilization of each of the components, heterogeneous version gives better utilization. It improves the compute utilization by 1.8 times, interconnect utilization by 3.1 times, and the configuration memory utilization by 3.9 times. Diagram on the right illustrates the power efficiency of the homogeneous versions and the corresponding heterogeneous versions. Address gives 2 times improvement, HiCube gives 1.6 times, SoftBrains gives 1.3 times improvement. If we use a subset of application kernels, it will generate a different heterogeneous CGRA with a better power efficiency. The graph shows normalized energy consumption of individual applications on the generated architectures. The values are normalized with respect to the energy consumption of the corresponding homogeneous version. All the applications give more than 20% reduction with maximum around 50% on address. This averages to around 40% reduction across architectures. We also performed analysis with REVAMP using applications from few prominent domains. Table shows the selected applications and their domains. Each application contains one or more computationally intensive kernels. We extract those kernels from each application and form the kernel suite which is provided as input to the REVAMP framework. For example, DNet 5 and MobileNet V1 applications, the input kernel suite contains 3 kernels: convolution, general matrix multiplication, and average pooling. Once these kernels are fed to REVAMP with homogeneous HiCube as the reference homogeneous CGRA, it generates heterogeneous architectures corresponding to each. The graph shows the normalized energy of kernels running on the derived heterogeneous architectures, where there is up to 40% reduction in the energy. REVAMP toolchain is available open source. Please scan the QR code for the link. Thank you for your participation.